Okay, hello, good afternoon. So last meeting, we discussed the bending stresses and the shear stresses of beams. And also we discussed the requirements for the design of beams. We have four, di ba? Yung major na four, and yung panglima is yung bearing, which is depende sa design ng support. Yung apat na yun, we have the strength base and yung serviceability requirement. Okay, dun sa strength requirement, we have your beam and shear. Okay, then the serviceability requirements, we have the deflection and lateral stability. Okay, so in this topic, we will discuss allowable stresses. So nabanggit ko during the last meeting that if our beam is not laterally stable, the bending capacity is not fully hindi ma-reach, not fully reach yung full potential bending capacity kasi nga hindi stable yung beams natin. So just like dun sa steel design natin, if our beams is not laterally stable, yung hindi natin ma-reach yung plastic moment, di ba? So same scenario when timber beams or when we are designing timbers. So kapag hindi laterally stable yung beams natin, hindi ma-reach yung full potential or full capacity of your bending stresses or bending capacity. Okay, so in this module, we will discuss allowable stresses based on the NCP 2015. Okay, so in the specs of the NCP 2015, you can see chapter 6. Okay, under chapter 6, you have your wood. Okay, dito sa wood na to nakapaloob yung National Structural Code of the Philippines. Okay, so volume 1, building towers and other vertical structures. Okay, so if you check the table 615.2-1, you have the reference values for visually stressed, graded, unseasoned timbers. Okay, so if you check this table, nakapaloob dito what are the capacity of different size of different group of timber species known in the Philippines. So actually hinahati siya sa sa four. We have the high strength group, we have the moderately high strength group, we have the medium strength group, and moderately low strength group. Okay, so first column, pinapakita dito yung bending and tension parallel to the grain. So these are the capacity in megapascal of our timber beams against bending and tension parallel to the grain. So next is we have the modulus of elasticity raised times 10 raised to 3 megapascal, written as times 10 raised to 3 megapascal. So ito yung ginagamit nating modulus of elasticity E. So ito yung properties of your timber beams. Or sorry, timber na gagamitin mo. Ito yung modulus of elasticity niya. So properties niya yan. Okay, at the third column, you have your compression parallel to the grain. So ito yung stresses, compression parallel to the grain. So if your orientation of your column, which is parallel to the grain, this is the capacity. Okay, the third column. At the fourth column, this is compression perpendicular to the grain. So if the arrangement of your fibers is perpendicular to the line of action or the compression, so ito yung gagamitin mong capacity. So as you can see, the compression parallel to the grain is always less than the compression parallel to the grain. Okay, so more on this if we discuss the design of column under timber beams. Under timber, sorry. Okay, and fifth, 1, 2, 3, 4, 5. In the fifth column, we have the shear capacity of our timbers parallel to the grain. Okay, this one. Okay, so yung itong taas, this one, is the stress of your grade. So ito yung quality of your grade dun sa timbers, sa wood mo, sa species ng wood mo. So sinabi dito that is 80% stress grade. And this column, this one, yan, this is the species or the common botanical names of your timbers. Okay, this is this table all about. Okay, the table 615.2-1. Okay, so other grade, you have the 63% stress grade. Okay, so if you are using a 63% stress grade of your timber of the wood, ito yung ating capacity. So the same, it was divided into 4 groups: high strength, moderately high strength, medium strength, and moderately low strength group. Okay, then the same na you have your 5 columns. Okay, and also we have a 50% stress grade. So 80, 63, and 50% stress grade. Okay, so under the 53%, 50% stress grade, the same siya. So bending and tension, ito yung stress capacity, full capacity when using 50% stress grade. This one is the modulus of elasticity. This one is the compression parallel, compression perpendicular, and shear parallel to the grain. Okay, so another reference values for unseasoned. Okay, take note, unseasoned. Okay, so unseasoned din to. So this one is the table for reference values for visually graded unseasoned timbers. So ito yung mga commercial species na nabibili, and this one is yung mga lesser known species. So hindi to ganun na nakikita or common sa market, sa yung mga ansowan, arangen, bansilay, and satinwood. Okay? So ito yung mga typical wood na lesser known species. Okay, more of that in this table, 615.2-2, this one, showing the 80% stress grade and 50% stress grade, additional species. Okay, ito yung mga additional species and additional species, 80% and 50% stress grade. Okay, so this one also for medium strength group, additional species. Okay, this one and this one. Okay, so yan. So if you are if you want to be a structural engineer, and also if you know a structural engineer that na hindi alam kung saan hahanapin yung capacity of the timbers, you can say that pwede mo siyang advise na check the table 615.2-2 of NSCP 2015. Okay, so all of these values is known to be ito yung mga values or the capacity at full tawag dito, at full capacity. Ibig sabihin, they are laterally stable. So they reach their full capacity since the beams is laterally stable. So mangyayari lang to, magagamit natin tong mga stresses na to if our beams is laterally stable. So take note, I will write it down. Okay, if the beams are laterally stable, FB is equals to the beams reach the full capacity. The beam reach its full capacity. Okay, ano bang problema sa full capacity? Okay, there's something wrong. Hindi gumagana yung aking XP pen. Full capacity. Bakit ganun? Okay. Anyway. So yun. So if the beams are laterally stable, the beam reach its full capacity. Okay, so mangyayari yon if the beams is full capacity. Okay, so the requirements, if we recall the requirements for the design of your timber beams, we have 4. Okay, so based on bending and flexure, based on shear, based on deflection, and based on lateral stability. Okay, so hindi natin na-discuss yung lateral stability, but we discuss ano yung common practice that can use lateral stability. Di ba? We have solid blocking and we have skewed blocking and also yung bridging, di ba? Na tinatawag. So ito yung mga common ways to restrain lateral movement in the timber beams to restrain the inherent torsion in your beams. And laterally unstable timber beams reduces the flexural capacity of the beams. So it can be categorized as maybe a short unbraced beam, an intermediate unbraced beam, or a long unbraced beams. Okay, so for the allowable bending stress, so as we all know that this topic is all about allowable bending stress. So under the allowable bending stress, FB prime, there is equals to the factor of adjustment or yung adjustment factor mo multiplied by the FB or the NECP 2015 table for the values, yung pinakita ko kanina. So all of these the bending capacity, okay, FB bending capacity will be reduces to some factor of adjustment. Okay, so what are the factors of adjustment? So we have the size factor adjustment, we have the form factor adjustment, and we have the lateral stability adjustment. Okay, so under these allowable bending stresses, we have three. So dito muna tayo sa number 1. Okay, so for number 1, we have the size factor adjustments. So when the depth of the rectangular sawn lumber bending member is from 125 mm or thicker and exceeds to 300 mm, the allowable bending stress FB shall be multiplied by the size factor CF. Okay? So ang nangyayari kasi if the beams is thicker or if the beams the depth of the beams is exceeds 300 mm or approximately ilan ba siya? 300 mm or 12 inches, meron na kasing size factor adjustment dun sa beams natin since the timbers is not fully when compared to steel, yung fibers niya is not ganon ka-compact since natural siya. So parang meron siyang adjustment when exceeds to 300 millimeters. So there is adjustment for the bending stresses for the FB, and we call that factor as C sub F. Ito yung factor niya. So yung C sub F is the size factor adjustment. Okay, what is the formula for the size factor adjustment? So the formula for the size factor adjustment is given by 300 over D raised to 1 over 9, whereas yung D mo shall be in millimeters. Okay, the depth of the beam shall be in millimeters. Okay, so the size factor adjustment, C sub F, is equals to 300 over D raised to 1 over 9. Okay, so for beams of circular section having a diameter greater than 340 millimeters, okay, the size factor CF may be determined on the basis on an equivalent conventional loaded rectangular sawn lumber beam. Okay, so kapag ang given yung circle, okay, this one is for So this one is for rectangular or square shape. Should be square shape. Okay, so if your timber beams is a rectangular square shape, this formula will be used. So C sub F is equals to 300 over D raised to 1 over 9. However, if your beams if your timber beams is a circular section, so you will use the same formula. Okay, you will use the same formula. However, your D, your depth of the beam na ipapasok mo dun sa formula shall be determined basis on equivalent conventional rectangular sawn lumber beam. So in other words, dapat yung ilalagay mong diameter D shall be the same area to your area of the circle. So parang kinonvert mo lang yung area of the circle to kinonvert lang natin yung area of circle, this one, area of circle, to equivalent area of rectangle or a square shape. Okay, so equivalent area of the circle to equivalent dimension in rectangle. So parang mangyayari, hanapin mo yung area of the circle. Okay, if you get the area of the circle and determine the length, that is also the same for the area of a rectangle, and determine the dimensions. So parang ganito siya. So what is the area of the area of the circle shall be equal to the area of the area of the triangle of the circle. Okay? So area of a square or a rectangle is given by d squared. Okay? Let's say depth of the beam, the same na lang, the same sila, since they are square. So small letter d, yun na lalagay ko. This one. Okay? D squared is equals to the area of the circle in terms of diameter, that is equals to pi d squared over 4. Okay? So taking square root both sides, you have the d is equals to square root of pi d square over 4. So ito yung diameter na ilalagay nyo sa formula dito. So hindi siya directly na kung ano yung diameter, yun na yung ilalagay mo. Hindi. So you need to convert your diameter of the diameter to an equivalent depth of the beam. Okay? So take note, the size factor shall not be used to visually graded lumber between 50 mm to 100 mm thick or a machine stress rated lumber. So hindi pwedeng gumamit ng size factor. You cannot reduce. The code is not permitted to reduce reduce the capacity for a 50 mm to 100 mm thick. Okay? And also for a machine stress rated lumber. So yung ginamit dito sa kanyang sa paggamit sa kanya is a machine stress lumber. Machine stress rated lumber. Okay? So that is all about for the size factor adjustment. So for another factor adjustment, we have the form factor adjustment. So under the form factor adjustments, so since the actual timbers are not perfectly formed, okay? So hindi naman kasi perfectly form yung ating timbers or the timbers kasi if circle, hindi naman yan perfect circle. Kapag square, hindi naman yan perfectly square. Meron siyang since human yung nagka-cut or human error, there are presence of human error. So hindi siya perfectly formed. So there is an adjustment factor, or there is a factor of adjustment that will be used for the capacity of your timber beams. Okay, therefore, so kapag meron kang form, we say that is a form factor. So if your beam section is a square or a rectangle, the form factor is equivalent to 1.414. So in-increase natin siya. Okay? So if your beam section is a circular shape, we will use a form factor that is equivalent to 1.180. So the form factor shall be cumulative with the size factor adjustment except for lumber I-beams and box beams. So yung form factor adjustment natin can be cumulative with the size factor adjustment. So kung if you want to consider the form factor, the same with the size factor adjustment, you can use at the same time. So pwedeng two-factor adjustment yung ginawa mo. So you will use the size factor adjustment. Okay, the size factor adjustment multiplied by the form factor adjustment. Okay, multiply by your the capacity of your timber beams, the bending capacity of your timber beams is equals to FB prime, or yung adjusted bending capacity. Okay, so that is the first two factors that we need to consider. Okay, so letter C is the lateral stability. So under the factors for the lateral stability, so CS is equivalent to the slenderness ratio. So recall the slenderness ratio tell us that which axis is more susceptible in bending. Okay, so yun yung ating, di ba, remember in steel design we have KL over R. Okay, so in terms of x-axis or in terms of y-axis. So the greater slenderness ratio will give you ito yung place na kung saan mas susceptible yung bending. sa axis na yon. Okay, in this lateral stability naman sa timber beams, one formula lang yung given. So the formula is square root of LE, okay, L sub E multiplied by depth of the beam divided by the breadth of the beam or the width of the beam. Okay, so the width of the beam is also known as the breadth of the beam or the breadth, I think that is the breadth of the beam. Okay, so ito yung width of the beam. Okay, so the slenderness ratio is given by square root of LE D over B squared. Whereas yung LE natin is the effective length of the beam. So if you recall that if we design the compression member, di ba, meron tayong mga K values. So iba-iba yung K values natin depende sa type of support, di ba? So K natin, remember, kapag pin, 1.0, kapag fixed, that is 0.5, kapag fixed free, that is 2.0. Okay? So ito, iba-iba yung values of K when yung K na yan, that is the distance of the contraflexure. Okay, that is this one. Kapag fixed. So ito lang yung effective length, this one. Okay? So pag full pin naman, okay, if you recall, this one, recalling lang tayo. So kapag ano naman, ganito, okay, ganyan. So full 1.0. Okay, this one is 0.5 L. This one is 1.0 L. Okay, so the same scenario in the lateral stability. So under lateral stability, the effective length is determined depending on the type of support and the loads that carrying ng beam natin. So kapag a single span beam, load concentrated at the center, the effective length is 1.61 LU, whereas yung LU mo is the unsupported length of the beam. Okay, then the single span beam, an uniformly distributed load, that is 1.92 LU. So single span beam, uniformly distributed load. So most of the time, you will be using this factor. Okay. So next is the single span beam, equal end moments. You have this formula, 1.84 LU. Cantilever beam loaded with concentrated at unsupported ends. You have your 1.69 LU. A cantilever beam with uniformly distributed load, that is 1.06 LU. And a cantilever beam uniformly distributed load with a concentrated load at the cantilever end. So the effective length is equals to LU. And lastly, the single span or cantilever beam of any other load, L sub E is equals to LU. Okay, whereas yung LU is the unsupported length of the beam. Okay, so now you have your slenderness ratio. So that slenderness ratio will tell us if our beam is short unbraced, intermediate unbraced, and long unbraced. So yung CS, okay, just like the timber design, sa steel design, yung slenderness ratio or the C sub S will tell us if, okay, will give you an answer, okay, will give you an answer if our beam is short, if our beam is intermediate unbraced, or if our beam is long unbraced. So this will tell you kung saan ba siya nabibilang. Okay? So if your slenderness ratio is less than 10, okay? If your slenderness ratio na na-compute mo dito is less than 10, the allowable bending stresses FB prime is equals to the values written in your NCP manual. So, ibig sabihin, no factor adjustment. Ibig sabihin, 100% or 1.0 yung factor of adjustment. Okay? So, ibig sabihin, full capacity marireach ng beam natin, yung kanyang bending, maximum capacity or yung bending stress niya. Okay? If your slenderness ratio is less than 10. Okay. However, if your slenderness ratio is greater than 10 but still less than C sub K, so in mathematical notation, that is CS is greater than 10 but less than C sub K, the formula is given by this table, this formula. So this formula is FB prime or the adjusted factor bending stresses is equals to FB multiplied by 1 minus 1/3 CS over C sub K raised to 4. Okay? So ano ba yung C sub K? So yung C sub K is dalawa. Nahahati siya sa dalawa. Kapag yung beams mo is visually graded, ibig sabihin, full, hindi ka naglagay ng glue, hindi mo sila dinikit. So as in 1-3 lang lahat yan. So that is 1-3. So hindi yan galing sa ibang tree, pinagdugtong mo, dinikit mo, hindi ganon. That is full, galing sa isang puno lang. So the formula of C sub K is equivalent to 0.8211 square root of modulus of elasticity of the wood or the timber divided by the full bending capacity, FB. Okay, this one is the formula. However, if your beams is glued laminated or machine stress rated lumber, the formula for C sub K is 0.956 square root of E over FB. So, ano ba yung glued laminated? So, yung glued laminated class, meron kang planks. Okay? Dinikit mo sila isa-isa. So, you use structural epoxy, okay, glue mo sila isa-isa. Yan. So to form a full timber beam size. So yan. Pwede yan kasi ginagawa yan. Na dinidikit nila isa-isa ng either an structural epoxy or a structural glue. Okay. So yan. So that is a section, section. So that is a glued laminated beam. So the same formula naman sila. However, iba lang yung value ng C sub K. Okay, so that's it for the formula for the intermediate unbraced beam. Okay, so the question is, what if naman if your C sub S or yung slenderness ratio is greater than C sub K? So ang ibig sabihin, if your slenderness ratio is C sub K, that is a long unbraced beam. Okay, so what is the formula, sir, for long unbraced beam? So the formula is dalawa. Okay, dalawa ang formula for long unbraced beam. So same value ng C sub K, ha. So this formula is given by 0.438 E over CS squared kapag visually graded yung beam. And the formula is 0.609 E over CS squared for glued laminated beam or machine stress rated lumber. Okay? And take note, for constructability issue, dapat daw yung C sub S should not exceed 50. So ito yung recommended value of your C sub S. The C sub S should not exceed 50. Okay, kung mapapansin natin yung dalawang formula, which one is greater or which one is mas malaki? Mas malaki yung glued laminated beam. Bakit? Kasi nga ginamitan na yan ng structural epoxy. So if the beam is pinahiran of structural epoxy or glued laminated or glue laminated na pang dikit, mas malakas yan compared to naturally grown timber. Okay, that is a 0.438 compared to 0.609. Okay, so C sub S is your slenderness ratio. So 0.438 modulus of elasticity of the wood na gaginamit over the slenderness ratio squared and 0.609 E over the slenderness ratio squared. So that is the formula for the lateral stability. Okay? So ayan, tapos na tayo for the allowable bending stresses. So the three, the size factor adjustment, the form factor adjustment, and the lateral stability adjustment is all we need to find kapag magde-design tayo. So 'di ba, if you recall, balik tayo dito sa taas. If you recall, sa bending and flexion natin, dapat yung maximum demand capacity natin or yung required the maximum demand or required bending stress shall be less than by your capacity. Whereas yung capacity natin is meron pang factor of adjustment or adjustment factor. Okay, so that's it. So I think we're now ready to solve for the following example problem. Okay, so let's try this example problem 1. So in this example problem, a single span beam having a span of 6 meters has a cross-section of 200 mm by 500 mm. So it carries a uniformly distributed load throughout its span. So the beam is made up of visually stress graded unseasoned apitong, 80% stress grade with an allowable bending stress of 16.5 megapascal and the modulus of elasticity of 7310 megapascal. Okay, so if you check na apitong, that is 80% grade. So check mo lang yun dito sa ating okay, nandito yan eh. That is that in this additional species. So dito siya sa species 80% grade. Ito. So medium strength group yun eh. So under this medium strength group, apitong, okay, so 16.5 and the modulus of elasticity na 7.31 times 10 raised to 3 or 7310. So which is exactly the same, dun sa ating example problem. So yung values pala na binigay niya is non-factor or walang adjustment. So ito yung allowable bending stress niya. So walang adjustment to. 16.5 and 7310. So if we rewrite that in a given, that is yung FB natin is 16.5 megapascal and the modulus of elasticity of the wood is 7310 megapascal. Okay, so the question 1, what is the slenderness factor of the beam? Okay, the C sub S, and compute the allowable bending stresses considering only the nominal dimensions, okay, and based only on lateral stability factor. Okay, so nominal dimensions yung ginamit and only on the lateral stability factor. So yung pangatlo lang. Ito lang yung pinapa-consider niya sa problem. Okay, so let's try to solve. So number 1, what is the slenderness factor of the beam? Ayun pala, pinakita ko pala dito yung high strength 16.5. Okay. So anyway, so what is how to solve for the slenderness factor of the beam? So according to the problem, a single span beam is actually tawag dito a single span or simply supported lang siya na 6 meter long and carrying a uniformly distributed load. So ang itsura niyan is ganito. Okay, bakit ganon? Pag nasa ilalim hindi gumagana. Anyway, so ang itsura niya ganito. This one. Carrying a uniformly distributed load having a span of 6 meters. Okay, so that is the beam natin. Okay, this one is our beam. Okay, so if we check the capacity or the effective length pala, sorry, if we check the effective length table na pinakita ko kanina, pumapasok siya dito, single span beam with a uniformly distributed load. So therefore, the effective length L sub E is given by this formula, 1.92 LU. So sinabi ko nga, ito yung most of the time na ginagamit nating formula. So 1.92 LU. Okay? So therefore, yung L sub E natin is 1.92 LU. Yung LU is the unsupported length of the beam. Therefore, LE is equals to 1.92 times 6, which is exactly the same, which is exactly equals to 11.52 meters. Tama ba ako? So I think yes. Oo nga, 11.52 meters. Okay, so now we're ready to solve for the slenderness factor. So for the slenderness factor, formula is equivalent to square root of LE times the diameter, times the depth of the beam divided by the width of the beams, the squared of the width of the beam or the breadth of the beam squared. Okay, so pasok lang natin. So take note, we are only considering the nominal dimension. So ibig sabihin, hindi tayo gagamit ng dress dimension. Okay, sige. So to solve for the slenderness factor, that is equivalent to 11.52. So I am using millimeters lahat. So the length LE is multiplied by 1,000. So 11.52 multiplied by 1,000 multiplied by the depth of the beam, which is 500, divided by the width of the beam is 200 squared. Okay, therefore, yung slenderness factor is 12. Okay? Ito yung ating slenderness factor C sub S. Okay, so now, okay na tayo dito sa problem 1. So the problem 2 naman is what is the allowable bending stresses? Okay, so to solve for the allowable bending stresses, we are ready to compare the slenderness factor to the three cases natin. Whether that is a short, that is an intermediate, or that is a long beam. Okay, so compare, check muna natin if greater than 10. So that is greater than 10, so hindi na siya pasok dito sa short and braced beam since our slenderness ratio is 12. Okay, so check natin yung C sub K. Okay. The formula for C sub K when visually graded sunbeams, so hindi binanggit na glue laminated siya. So automatically that is the visually graded sunbeams. So the formula C sub K is equivalent to 0.811 square root of E over FB, whereas yung E mo is the modulus of elasticity, which is equivalent to 7310 megapascal. And yung FB mo is the full capacity of your 80% graded apitong. Okay, so that is based on the table na 16.5 megapascal. So that is equivalent to 16.5 megapascal. Okay, so yan, pwede na natin ipasok sa formula for the C sub K. So to solve for C sub K, that is equivalent to 0.811 square root of 7310 divided by 16.5. So all in terms of megapascal, your C sub K is now equals to 17.1. Okay, so if we check, C sub S is between 10 to C sub K, which is 17.1. So ito ay 12. So therefore, we can say that our beam is intermediate unbraced beam. Dito siya pumapasok sa intermediate unbraced beam. Okay, so pasok na natin sa formula. So the formula FB prime is equivalent to FB, multiplied by 1 minus 1/3 C sub S over C sub K raised to 4. Okay, so FB natin is 16.5 multiplied by 1 minus 1/3, 12 over 17.1 raised to 4. Okay, therefore, yung allowable bending stress mo adjusted is equivalent to 15.2 megapascal. Okay, so yan yung how to solve for the allowable bending stress based on lateral stability. Okay, next problem, example problem 2. So a wooden beam having a width of 200 millimeters and a depth of 350 millimeters and has a simple span of 6 meters. So if the weight of the beam is 6.3 kilonewton per cubic meter, so additional to its load, na binubuhat niya in terms of W, additional to that, the allowable bending shear stress is R10.7 and 0.7 megapascal respectively. So ibig sabihin ay may binubuhat siya na W, may binubuhat siyang W, and that W may additional pa na weight of the beam, 6.3 kilonewton per cubic meter. So given the moment max for simply supported, I think you are now familiar with WL squared over 8. And maximum shear, you are now familiar with the maximum shear, which is WL over 2 for simply supported beams. So ito yung formula natin. Okay, so problem 1, what is the size factor adjustment to the allowable bending stress? Number 2, what is the safe uniform load that the beam can support based on the flexural bending strength with size factor adjustment only? And letter C, what is the safe uniform load that the beam could support based on the shear strength only? Okay, sige. So for number 1, what is the size factor adjustment? So since the depth of the beams exceeds to 300 millimeters and not less than 125 millimeters, we can use the formula C sub S equals to 300 over D raised to 1 over 9. Whereas yung D natin, so since that is a rectangle, so the same. Kung ano yung D natin or yung depth ng beam, yun yung gagamitin natin full. So since the depth of the beam natin is 350, so that the pasok siya dito sa exceeding by 300 mm. So therefore, C sub S is equals to 300 over 350 raised to 1 over 9. That is equivalent to 0.983. So ito yung adjustment factor based on size na gagamitin natin for the allowable bending stress. Okay? So next natin is next problem, what is the safe uniform load that the beam could support based on the flexural bending strength with a size factor adjustment only? So as we all know, to be safe, to be determine if the beam is safe or adequate, we need to equate the demand or the required moment or the required bending stress to the capacity or to the strength. Okay, so we need to equate. Okay, so back on module 17, I discussed the formula for the maximum bending stress 6 for a rectangular shape that is equivalent to 6m over bd squared. Okay, so rectangular 6m over bd squared shall be less than or equal to the capacity of your timber beams. Okay, so going back to the formula, okay, 6 multiplied by m over 200 times 350 squared, and now we now have your factor adjustment na 0.983. This one is the factor adjustment based on size, that is C sub S, and this one is the full bending capacity na 10.6. Okay, so this should be, sino ba yung tama? Okay, so this should be 10. Okay, I think meron akong typo error. So this should be 10. So tama pala to, na dapat ito ay 10, hindi siya 10.6. This should be 10. Okay. Anyway, so that is 10. Okay? So C sub S, so FB prime natin, di ba? FB prime natin or adjusted bending capacity is equals to C sub S or the factor na we only considering, since the problem is only considering size factor adjustment multiplied by FB. Okay? So that is 0.983 times 10. That is to solve for the moment M. So 0.983 times 10 times 200 over 350 squared divided by 6. Okay, nakalimutan ko yung 6 dito. So divided by 6. So 200 times 350 squared times 0.983 times 10 divided by 6. You now have 425 47516. So this is 10.6 pala talaga. So okay, sorry. So tama pala to na this one is 10.6 and this one is correct. This should be 10.6. Okay? Sorry. So that is 10.6 and dito may divided by 6 to get your moment. Okay? So 0.983 multiplied by 10.6 multiplied by 200 times 350 squared divided by 6, you get 42.5 million or 42.5 million Newton millimeters. So 42.5 million Newton millimeters. So ito yung full moment na kaya niya lang buhatin. Okay. So what is W? Okay. So ano ba yung load W na binubuhat niya. So you just simply equate the maximum moment to the formula WL squared over 8. So kasi ito yung moment na to, ito lang yung based on the strength. Ito lang yung kaya niyang buhatin na moment. Then you compare that to your actual loading, so WL squared over 8. So you get your W na 42.5 times 8 over 6 squared. That is equivalent to 9.44 kilonewton per meter. So no need to worry about this mga units. So pwede mong gawin ganito ka. Pwede mong gawin in terms of Newton millimeters lahat. So 42.5 times 10 raised to 6 is equals to W multiplied by 6,000 squared divided by 8. You get your W in terms of Newton per meter. Millimeter, sorry. Newton per millimeter. So just simply convert that to kilonewton meter. So 42.56 times 8 over 6,000 squared. So exactly the same sila. So last meeting na discuss ko what is the conversion, di ba? A Newton per millimeter is equivalent to 1 kilonewton per meter. So 1,000 times 1,000 divide 1,000. So exactly times 1 lang siya. So they are the same. Okay, so that is 9.44 kilonewton per meter. So ito yung total W na kaya niyang buhatin. So yung W na yan, paghahatian niya ng self-weight and yung other load na bubuhatin niya, excluded yung beam weight niya. So first is hanapin natin yung beam weight. So kapag nahanap natin yung beam weight, minus natin dito. So ito yung full na weight na kaya niyang buhatin. Sorry, full W na kaya niyang buhatin. So the weight of the beam is equals to in terms of Newton per kilonewton per meter, since kilonewton per meter ang nilagay ko dito. So convert nyo lang lahat. So ito ay 6.3 kilonewton per cubic meter multiplied by that to the area of the beam. So 0.2 meters by 0.35 meters. Okay, 200 by 350 mm. So 1,000 mm, 1 meter. Okay, so you get the weight of the beam na 0.44 kilonewton per meter. So that is the total weight of your beam. Okay? So 9.44 minus the 0.44, you get 9 kilonewton per cubic meter. So yung 9 kilonewton per cubic meter is the maximum safe uniform load that the beam could support based only on the flexural bending stress adjusted by the size factor. Okay? So the problem C, okay, what is now the safe uniform load naman based on the shear strength capacity. So as we all know, given yung capacity natin na 0.7 megapascal shear capacity parallel to the grain. So back on module 17, the maximum shear stress of a rectangular shape is 3V over 2A, whereas the A is B times D. Okay, if you recall the formula. So 3V times over 2BD is equals to 0.7. So solve for V, that is equivalent. So 2 times B times D divided by 3. So 0.7 times 2 times B times 350 divided by 3, that is equivalent to 32,667 newtons. Okay, so converting that to kilonewton, that is divided by 1,000, that is 32.667 kilonewtons. Okay, so based on the based on the formula, WL over 2 is the maximum shear. Okay, so it's just simply V is equals to WL over 2. So since we need to find W, so ganun din yung path natin. Hanapin natin yung W, minusan mo ng weight of the beam, that is the safe uniform load. Okay? So ganun din yung path natin ng pagsosolve. So equate lang natin yung 32.667 by the WL over 2. So 32.667 times W times 6 over 2. Okay, so 32.667 times 2 divided by 6, that is 10.89 kilonewton per meter. So therefore, The safe uniform load W, so 10.89 minus the self weight of the beam, which is 0.44, you get 10.45 kilonewton per meter. Okay, this sorry for the typographical error. This should be kilonewton per meter. Okay, so that's all for this module. So allowable stresses. Okay, so if you find the reference, you can check Structural Timber Design by Abdi Kermani, Structural Design in Wood by the Stockner JJ, and Timber Design by the Vesabilia, and the NSCP 2015 ASEP. And some problems, okay, I think the Problem 2 is based on the PRC Civil Engineering Board Exam 2006. I think ito ko kinuha yun eh. Sa Board Exam 2006. Okay? Sige. So enough for this topic. So see you next meeting.